I'm going to start recording, and we're going to start up the lecture. This will be an extension from the videos that we that I had posted for Monday. Okay, so I'm going to start from this one actually because it's just an easier place to start from, even though that technically it would have been in the end of that video. Okay, but I want you to have it fresh in your head. So right here, this is sort of the flow you want to look at whenever you're trying to use infrared to further elucidate the structure of a molecule. Remember that when you're looking at structures of molecules, it's typically going to be information from another source, like another spectroscopy, and then information from the spectroscopy we're looking at right now, which is the infrared. Okay? Rarely would you be able to just take a molecule and know the exact structure with no other information, just one spectra, okay? These three spectra together, the mass spectroscopy, the infrared spectroscopy, and the NMR later, those are going to be able to go a completely unknown structure to, hey, this is what it is, okay? Not a single one of those at all, right? Okay. So the flow you should always consider, and again, that's that same thing we had talked about from mass spectroscopy, right? There's a flow to these things. When you're trying to solve a problem, there's always a structure that is best to solving that problem, right? Okay, whether it is a crime scene, whether it is a spectra, okay? Okay, so you're going to look at your spectra. You're going to go above 1400 wave numbers. This would be things like 3000, 2,900, 2,100, okay? And you're going to identify those peaks. What functional groups do those peaks indicate, okay? Some of them only really have one option, but some of them could be two things that are fairly close together, okay? So for example, like carbon hydrogens are very easy to figure out. OHs are very easy to figure out. NHs are very easy to figure out. And so that's going to give you a lot of information just from that. They're very easy compared to the other stuff we're going to look at. Okay? So again, we're going to see that certain bonds are present. You really want to look, especially for the presence or absence of peaks that we would see in 16.6. Those would be examples of those peaks. And what we would see is things like an OH bond. That's the OH stretching motion. That has a very broad, very strong peak, extremely obvious. It really is unmistakable for anything else. Okay? And you can very easily see there's multiples of those because you'd see peaks for each one. NH peaks, again, that actually really helps you out with finding NH peaks. Again, it's not very mistakable for the OH because it's much sharper. It's not as broad. Okay? So if you look at those peaks and kind of get a database in your head going on, at least being able to remember the general peak shapes and locations, you're going to be able to identify those pretty easily. Okay? And then there's the carbon-oxygen double bond, the carbon-carbon double bond, and then the carbon-carbon triple bond, CN triple bond, and the CHs, of course. You're going to have a lot of CHs, so they're not going to give you as much information. But if you have something like all the CHs are located where benzene CHs should be, well, then you know, yeah, benzene, don't you? Or a benzene derivative. Okay? And so these very much can help you elucidate, like, do I have a benzene? Do I have an H next to a double bond? Those sort of things. Okay, now, the next part that we want to look at is we want to consider functional groups that have more than one type of bond that we've identified in step 1. So, for example, do you have a combination of two functional groups that interfere with each other? Okay. So what you'll get is shifts for where those functional groups bands are. So for example, if you have a carbon-oxygen double bond and an OH bond, you could have a carboxylic acid. Okay? So that should be something that's in your head. I should look and see if I have a carboxylic acid. They could be separate, or they could be together in a carboxylic acid, right? Okay. So another one would be a carbonyl CO double bond and an NH. This would be an amide. if you have them on the same area, right? You have them connected to the same carbon, that they're interfering with each other. Okay? And so you want to consider amides if you have these two bands that you've identified from here. This right here would be an aldehyde. That would be a CO double bond with a CH. That's 2720 and 2820 around to those two wave numbers. See how far that's shifted? That's considerably shifted off the normal 2900s, right? And so you would see this CH bond that has two. They'd be somewhat similar, and they'd be about 100 wave numbers apart, 2720, 2820. And this would give you evidence that, hey, I have an aldehyde instead of a ketone for that CO double bond. Okay? This right here then would be an alkene or an aromatic ring that we might be looking at. This would be evidence of a CC double bond. And then we have a CH that's shifted upwards, higher wave numbers. And this would give us an alkene or an aromatic ring if we have a CC double bond that has a CH on it. This right here would be a CC triple bond, and this would be a CH. This would give us a band that's somewhere around 3,300. Again, it's going to be pretty influenceable by other functional groups, but 3,300-ish. This tells you have a terminal alkane because carbons can only have 4 bonds. And so one of those carbons has to have a hydrogen, right? Meaning it's a terminal. Okay, so what do we look at for next? Well, we look for the special characteristics of absorption peaks that we've identified in our step 1. So is the OH absorption consistent with an alcohol or a carboxylic acid? Does it look like the alcohol or carboxylic acid? Notice that we're going finer and finer details of these as we go along, right? So you may get this part right here, which would give you the information of what type of bond you have, right? And it would limit the functional groups that you have, okay? You'll need to understand more and have a more precise understanding of where those functional groups would show up on the wave numbers to get this next part, right? Which is that combination functional groups. Did they interfere with each other? So this right here, they have interfered with each other, right? This carbon-hydrogen is being changed by the triple bond, okay? And that tells you that they're connected, doesn't it? And so if you understand more about it, then you can look at the shape of the peak. This is a more difficult thing. You do not have to actually get all of these to get information, though, right? Every step of this gives you more information, okay? For example, at this point, we know the broad functional groups. Remember that headings that we always talked about, like, we're doing carbonyl bonds now. Yeah, that stuff, right? This gives you the finer details of functional groups, okay? And this one here gives you even more information about them, right? So we can then determine more specifically and build more information. Do we have a carboxylic acid or do we have an alcohol? Do we have a NH absorption that would be consistent with an H, just one hydrogen? Or do we have one that's consistent with having 2 hydrogens on there? Okay. Why didn't I, what would happen if we didn't have any hydrogens on there, by the way? Yeah, no NH, right? Yeah, just NH. So we wouldn't have any NH that would show up in the spectra. So does the frequency of the CO absorption, that's the double bond, suggest a carboxylic acid? Does it suggest an ester? Does it suggest a ketone, aldehyde, an amide? All of those are going to cause frequency shifts, okay? Right. So these are all things that you need to consider whenever you're looking at this spectra. This would be, again, the finer details. Does it mean that if you don't see these details that you can't do anything with spectra? No. Okay? You can still get the previous steps. So the next thing would be establish whether a CO bond is conjugated. So your conjugated CO bond, this has to have a CC double bond as part of an alkene or an aromatic ring. And so this conjugation is going to lower that CO frequency by approximately 20 to 40 wave numbers. Okay. Do note that it can be a little bit challenging to get the amount of conjugation from this, because the 20 to 40 overlaps, doesn't it? If you had two 20s, they would be 40. It's pretty rare for that to happen, but every now and then it does trick you up. Okay? If you start using this for very, very precise calculations. You can calculate it, by the way. So if you're going into more advanced spectroscopy later on, you can actually calculate what it should be, and then you know essentially what sort of shift you should have. And so you can get how many conjugations you're seeing. Okay, so let's do an unknown. We have already ran our mass spectrometer, and we got C7H8O. Okay, so we've already gotten that chemical formula. So we have 7 carbons, 8 hydrogens, 1 oxygen. Okay, how they're arranged and connected, we don't know yet. That's what we're trying to figure out. All right. And so how do we go about figuring this out? Well, start going down the steps. Okay, so first thing we want to do is we want to figure out what our IHD is, right? What our hydrogen deficit is, okay? So what would a completely saturated molecule have in terms of hydrogens? Yeah, we'd have 2N plus 2, right? Okay, and so we would have that 16 hydrogen atoms if we were completely saturated. Okay, we do not have 16 hydrogen atoms, which means that we don't have it completely saturated, do we? Okay, so what would the IHD number be then in terms of how many like double bonds, how many triple bonds, that sort of thing? So what's our deficit of hydrogens? Yeah, so we take that number of the deficit, right, 8. So 16 minus 8. And then we divide it by 2. And that's going to give us our number of features that would be things like rings, things like a double bond, things like the triple bond portion. Okay, so that's 4 right there, right? Now, that actually gives us a pretty nice indicator. So we could have a few different things, right? We could have these be rings, double bonds, maybe even a triple bond that we're considering. But if we consider a ring and then double bonds like a benzene ring, right? Then that would be pretty close to our number, wouldn't it? Yeah, we very likely would have that number, wouldn't we? And so if we consider that, when you start seeing IHDs of like 4-ish, you might want to consider it, right? Benzene rings are very stable. They're very common. That'd be very likely. So again, a benzene ring would have the ring portion. That's 1 IHD. And that would have 3 double bonds, right? So that'd be 4 IHD altogether. 1 for the ring, because the ring connects back into itself. You're missing 2 hydrogens because of that. And then the double bond, each double bond means you're missing 2 hydrogens, right? And so an IHD of 4, 1 for the ring, 3 for the double bonds. Okay, so the next step we need to do here is going to be, we're going to look up here, right? Because this is above the 1400, right? So we want to look at these features up here. Look for the strongest features first, and then we can move to smaller features as we go. Okay? So what catches your attention right away? Something big should catch your attention up here. Huge band here, right? Very, very broad, right? Centered around 3,300 wave numbers. And so that right there would correspond with an OH. So we have an OH stretch, don't we? And so that oxygen there, it's an alcohol, isn't it? Okay? We don't have another oxygen, so we don't have to consider things like a carboxylic acid or any of that junk, right? So we're done with that. Cool. Okay, so the next one we want to consider here is we have these right here. Those would normally be consistent with what? These sharper, carbon-hydrogen bonds, right? So these would be carbon-hydrogen bonds. So CH stretches. Now, if we look at these, though, there's some of them are much higher than you normally see. Yeah, that's going to be our benzene ring, isn't it? If we have a benzene ring, or they'd be off an alkene. Okay, so that's more evidence that we have either a benzene ring or an alkene, right? Yeah. And we have a very consistent sort of set of bonds there, don't we? So, yeah, it gives more evidence that that ring structure makes a lot of sense, doesn't it? Okay. Now, the next one down we want to look at is going to be the ones that are a little bit closer to 1400 down here. And so these could be a few things, but they're very consistent with something we've already kind of mentioned before, right? Which would be a carbon-carbon double bond. And so these would be consistent with a carbon-carbon double bond. Okay? And so we have our carbon-carbon double bond, again, further reinforced, don't we? So we have a lot of evidence now that we have these carbon-carbon double bonds, and we have a pretty uniform set of them, because we don't have this like large splitting going on here. And that we have an OH off there somewhere. Okay? Okay. And so for the next thing we need to do here, we need to look a little bit further in detail. So we look at that absorption. That's our 3050 up here. We look down here again, and I've sort of already started doing this step because I wanted you to start thinking that way, right? And so those two items together give us very strong indicators, right? That we have these carbon-carbon double bonds with hydrogens on them, doesn't it? Okay. And so that's building evidence for that case, isn't it? Okay. All right, so the next thing we need to do is we need to figure out if those are an alkene or are they aromatic, right? That's the next thing we want to figure out, because we really want to know, hey, do we have alkenes that are individual? And so do we have like just more alkenes in a straight chain? Or do we have some triple bond mixed in there? We don't have any triple bond indicators, so that one's pretty limited. Notice the no triple bond up here. And so, well, now we need to figure out, is that going to be the alkene stretches and just a chain, or is that going to be individual ones? Is that going to be an aromatic ring? And so an alkene is typically going to exhibit one peak above 1620. So we'd come up here to 1620. The aromatic ring is typically going to be 1450 to 1600. And so we'd look here, 1450 down here to 1600 up here. And that pretty clearly demonstrates that we have a very conjugate system, doesn't it? Yeah. So again, if we had just individual double bonds, they would be a higher wave number. They'd be up here at 1620. See how shifted down they are? They're way further down in the wave numbers. So that tells you they're very conjugated. And they're so conjugated, it indicates that we have a benzene ring of some sort, an aromatic ring, right? So you can actually see in the table, it gives you separate places for those, so you don't have to know the conjugation as well. So if you look at the table of frequencies for functional groups, it actually separates out the aromatic rings. So that's consistent with an aromatic ring right there. Yeah, the two peaks right here and here actually both indicate the aromatic ring because you have the symmetric and anti-symmetric stretches. Okay, so we have the IHD of 4, and that's going to give us the, there's actually a set of 2 here as well. It's a doublet. Oh. Okay. So the IHD of 4, all that information about the aromatic ring, well, that and the number of carbons here, I mean, that really, really strongly indicates that we have a benzene ring, doesn't it? Yeah. So we have a benzene ring and apparently a methyl coming off there. One of the things we can look at here is see how we have these peaks right here? Those are a CH that are not on a benzene ring, aren't they? Yeah. And so that would be consistent with having some sort of methyl or something, right? Yeah. Exactly. Yep. Yep. You're putting those pieces together, and those are both very strong indicators, very strong evidence, right? That you got some sort of methyl coming off of that aromatic ring. Okay. Okay. So we've used 6 carbons then for the aromatic ring, right? That'd be your benzene. And then 1 carbon would be your methyl there. And that has to be then attached to that benzene in some way. And then we have an OH that's attached to that, don't we? Okay. So the next part we want to do is we want to also make sure and double check, cross our T's and dot our I's. Do we have these other groups that could also indicate something? So, for example, I've already indicated this one because it automatically goes through the steps from my mind. So whenever you look for this, double check if you have a carbon oxygen double bond. We don't have that, do we? No. So yeah, double check that we don't have a carbon oxygen double bond. Double check that you don't have one that's conjugated with the CC. That would lower the frequency a little bit. We don't even have anywhere close to it, so it's not even an issue. So because we don't have that, we don't really have to do anything about that. So we're kind of done. Now you're going to notice there's a few options that we have left, right? Again, a single spectroscopy isn't going to tell you everything about a molecule. And so there are a few options that you'd have left. What this would look like on a test question is if it was like open-ended, you'd have to put one of the options, okay? If it was a multiple choice, I would give you one of the options as an answer. And then you'd be like, oh, it has to be that. Kind of like what we did with the nitrogen. Automatically, you knew you had the amine, right? So, because it was an odd number, right? It's the only option with amine. You didn't have to go, which amine do I have? Yeah. So, these are the options that would all work for that. So, any of these would actually work. Funny enough, with enough expertise, I could sit down, I could do the calculations for the conjugation and then the shifts, and I could actually have strong evidence to separate these to some degree. So there is actually a way to separate them, but I'm not going to go on that with you guys because it's more of an advanced spectroscopy course that we'd have to go over. And we'd have to do a few different types of infrared spectroscopy. There's ways of changing the infrared spectroscopy. I just wanted you guys to have an idea. There's more to infrared spectroscopy than what I'm going to teach you in this course. Like, one chapter is not enough to encompass spectroscopy that's been in development for 200 years almost. Okay? So, a very common misconception organic courses tend to give you is like infrared Raman spectroscopy. There's nothing else to them. And then people are like, yeah, you just press a button. That's all there is to it. It's not all there is to it. There's a lot more. We just don't teach you everything in one chapter. It's not possible. Okay, so try this one. I want you to start first without me and see how far you can get along that step-by-step pathway. Huh? Yeah, right now we don't have enough information to separate. Yeah. And again, that's that 2 spectroscopy methods is probably not going to be enough to get the complete answer for these things. Okay, try this one. Again, we got our mass spectroscopy right there, which gave us our chemical formula. probably give you about 1 more minute. So that's about enough time for you to go, oh, I don't know what I'm doing, or I kind of know what I'm doing. I'm getting you to the point where I give up. Don't forget, if you get stuck on things, well, I'm going to take you through it here, but make sure you practice those. Make sure you practice the problems in the homework, because it's going to help you learn that puzzle solving techniques, right? You know, application is a big part. Kind of like, yeah, get better at solving puzzles and playing chess by solving puzzles and playing chess. Okay. So, first thing you should always do with these when you're given those chemical formulas, right? As soon as you see those chemical formulas, you're trying to figure out structure from them. That would be figuring out your IHD. Okay. It's not really step one of the infrared spectroscopy because it is more of the mass spectrometry portion. And so you have 8 carbons, 2 times that, 16, plus 2 would be 18, right? And so you see that it has 14 carbons, or hydrogens there, excuse me. And that means that we have an IHD of 2. So 4 hydrogens short, divided by 2, 2 hydrogens per group that you'd have. That would give you a 4. Okay. 2, excuse me. Now, when we have an IHD of 2, well, there's a few things that could be, right? We could have a ring would be 1 IHD each. That seems unlikely in this case. We'll get to why in just a bit. But we could have a triple bond. And again, that would be something that's easy to check, right? We just go down here. We check for that triple bond. No, not really. It's almost completely flat here, right? So, no, that seems very, very unlikely, doesn't it? Okay. Then we could have double bonds, couldn't we? And so those would be the next ones you'd want to check for. So that actually brings us into step 1 now. So we're going to look for the functional groups that are above 1400 and look for those and see what functional groups do those indicate. So notice that again, the absence of things is just as important as the presence, right? We have no big OH, do we? And so that tells us this is not an alcohol, right? So that helps us reinforce what that oxygen can be, okay? And so we would go down again from the top to the bottom usually. We see a bunch of like pretty tightly grouped carbon hydrogens, right? We don't see a lot of like higher or lower, that sort of stuff. Just a little bit higher right here, right? And then we have ones down here that are the normal carbon hydrogens, okay? And so that right there tells us we have 2 sets of carbon hydrogens, right? We have a 30-50 right there. That would indicate we have a carbon hydrogen off of a double bond, wouldn't it? Okay. This one right here would indicate that we have a carbon hydrogen off of a single bond. Okay. And so we have a pretty good case so far for something like an alkene, don't we? Okay. Okay, and so now we're going to go down further. And we see they're even labeled for us so we can see the wave numbers easier. 1682 and 1617 here. And so 1682 would be consistent with a carbon-oxygen double bond, wouldn't it? And 1617 would be consistent with a carbon-carbon stretch. Again, carbon-carbon double bond stretch. Okay. And so, again, we have a preponderance of evidence that's giving us we have a carbonyl, right? And we have a carbon-carbon double bond, okay? So the next part is going to be considering the compound class where the carbon-oxygen bond might be involved. Again, we don't have another oxygen, so carboxylic acid's obviously not possible. We can't have an ester because we don't have another oxygen. Again, that eliminating things does help you get to the final answers. We don't have to consider a mid because, again, there's no NH stretches here. There's no indication. There's no nitrogen. There's no indication of any of that. Okay. Now, in terms of aldehyde, we would want to look for the CH stretch at 2720 and 2820. And so we'd come here, down here, to 2720 and 2820, and we just don't see a peak, do we? Yeah. And so that very strongly tells us we probably don't have an aldehyde, because that would be the hydrogen off of that carbonyl with it. And so, we have those 3050. That's that CH on an alkene or aromatic. It could also be a case there, but we don't have enough carbon bonds for an aromatic. And we do have one 1617. That's again a CC double stretch. So again, those are those case that we're building up right there, right? So we have some sort of ketone with an alkene, don't we? So the next step here is going to be the frequency for the CC stretch at 1617. Now, this does suggest an alkene rather than an aromatic ring. It's not in the right place for the aromatic ring. Now, again, that aromatic ring would have multiple peaks, usually two, set of two, which would be the symmetric, antisymmetric, which would be that 1450 to 1600. And again, we don't have that. We just have that 1617 here. And so that, again, tells us, again, we don't have an aromatic ring. And again, even the IHD number didn't support an aromatic ring, okay? So again, we can eliminate that really. We actually have eliminated that through multiple fronts. Okay, now the CO stretch for the ketone normally appears at 1720, excuse me. That's lower, isn't it? Yeah, it's actually shifted down quite a bit at 1682. And so what that tells you is that sort of difference, which is about like a 40 wave number difference. Let me look at the table later. Yeah, that table is directly from your book. I'll have to double check it. But that may be indicating for the conjugated ones. I'll have to double check. So the high end for a CO double bond stretch would be the 1720, around 1720. It being shifted lower to 1682, this would indicate conjugation. Okay. And so that would be evidence that the carbon-carbon double bond and the carbon-oxygen double bond are conjugated, and meaning they're next to each other, right? Okay. So what would the options be for this structure? They would look like this. These would all be valid options for that structure. Okay. And so we have our ketone, we have our carbon-carbon double bond. They're conjugated because they're next to each other. And notice you can't put the ketone at the end of any of these because that would be an aldehyde. We know we don't have an aldehyde. We can have branching here. So that's one of the things that might not pop into your mind here. Yeah. Yeah, you could always flip them as well. Those would be the exact same structure here. So you don't actually have to write those out. Okay. Okay, so go ahead and try this on this problem right here. By the way, that last part where I was talking about the conjugation, you having multiple double bonds should always bring that question up to your head. Okay? So multiple double bonds, are they apart from each other? or are they next to each other connected? Hmm? Oh, is it? Whoops. Okay. Yeah, whoops. Well, now you know. Okay, do this one then. I have my things out of order apparently. One of the things I want you to keep in the back of your head that'll be useful if you ever actually have to do anything with infrared is band position is always king. Band intensity is always secondary. Okay? So the band position is always the more important thing. The band intensity is always the less important thing. Okay? It's still information. It's just not as important as the position. Okay. I'm going to go ahead and move on unless somebody's making really good progress. I'm not hearing any like debate or anything. Okay. So what's that first thing you want to look for? So the first thing you always want to do whenever you have these structures here, where you have the molecular formula, IHD. And so your IHD is what? 2. Perfect. Yeah. Okay. So the next thing we're going to go about is that's that step 1 for looking at these infrared spectra, right? And so we start up here and we kind of go downwards. One of the things you should take note of, you have these nitrogens and oxygens, right? Is always look here for what you're missing. Okay? Notice we don't have any intense bands here, do we? This is a big red flag that says we don't have an alcohol. We don't have an amine, something that has like an NH bond, right? We don't have any NH stretches here. Okay? And so it can't be an OH, it can't be an NH. We don't have any of that. Okay? Those would be right here. Us not having those intense bands means can't have it, right? Doesn't exist. Okay, so these next ones we have here, these are between 3,000 right here, and they go down to like 2,800 here. That one there. And that would be a big indicator that we have what type of bond there. We have alkane, CHs. So those are a very, very nice indicator we have CHs. Okay. And so now we kind of look down and we see, oh, we have a very like nice, sharp, intense peak, don't we? It's sort of medium to medium strong, right? Okay. It's not weak, not medium weak, that sort of thing. It's, pretty strong. Okay. And so that one right there is going to indicate us, well, this is some sort of triple bond, right? This could be a carbon-carbon triple bond. It could be a carbon-nitrogen triple bond by this position. Okay? You always want to consider the position first because, again, the position is always the more important one to consider. The intensity can build up cases if we have nothing else. Okay. So we're now going to start looking for knock-on effects of the functional groups that we already identified. So we identified we have some sort of triple bond, right? So if we have a triple bond with carbon-carbon, that would be a terminal at the end of a ring. We'd expect a CH stretch, and we'd expect it up here at 3,300, right? We don't have that, do we? Okay. And so we don't have that terminal carbon-carbon triple bond. Okay, that doesn't exist. Because again, we don't have the CH stretch that would have to be an effect of that. So if we have some sort of triple bond, it needs to be something that doesn't have a hydrogen coming off of it, right? Okay. So for the next step, we're going to look here at this peak, and this is where we would want to start going, well, we don't have any other information to go off of, so we're going to have to start going off of intensities. Okay? Again, if you have positional information, that's going to take precedence, right? It's more reliable. Okay. So this one right here is, again, a moderate intensity. It's not a weaker intensity, right? That indicates you have a larger dipole moment, meaning you have a larger difference in electronegativities. Okay? And so the carbon-nitrogen bond is going to be more likely than the carbon-carbon triple bond. Okay? So you probably have a CN triple bond. Right? That's what this intensity is telling us. The cases for it not being a CN triple bond are actually really weak. So we would very likely have a carbon-nitrogen triple bond there. Okay. And then we really don't have anything else that we need to consider there for that. So we don't really have any indications of rings. We don't have any indications of a carbon-oxygen double bond. That didn't show up anywhere here. We don't have any indications of any of these other functional groups, really, do we? Notice everything else shows up down here at like 1500 and below. That's very typical sort of bends that we would see. And carbon-carbon single bond stretches. Okay. And so, well, what does that add together to? It adds together to some sort of alkene. Notice again, the three options for the oxygen would have been an alcohol, right? We don't have no H. We don't have a carbon-oxygen double bond, do we? So we can't be that. And so that has to be an ether, doesn't it? Okay. And then we have this carbon-nitrogen triple bond. We have an IHD of 2. That's both evidence that we have that cyano group going. Okay, that CN triple bond. And so we go ahead and put those two together, and these would be our options. So these would both be likely structures for that. Okay. This one? No, not really. It could be off, further off. Yeah, there's, these are just two of the most likely options. Yeah, as long as you recognize that, yeah, we got the ether and the cyano. Those would be the big parts. Okay. So these right here are some characteristic frequencies of absorption in infrared spectroscopy. We have the different modes that we've talked about here. And again, these would be the number of bands you're likely to see for these. These would be the frequencies, and these would be the appearance. Now, this one I took from your book, and I'm trying to stay consistent with your book for this information, but know that organic textbooks for tables of physical characteristics are very, very notorious for having issues. Okay, there is a long-standing issue with the pKa for hydrogens that is for 40 years was wrong in all the organic textbooks. because they misunderstood the tables and other texts. So if you do find an issue, please send it to me, and I'll try to get together like a compendium of, hey, this is where your book has an issue. You can actually look it up versus the NIST has one. So NIST has a frequency table. I have no idea why all books don't just adopt the NIST one. So this is the one, I haven't yet actually had one where they're like, this is wrong. So I just haven't had a chance to go through and compare every single band from this book with the NIST table. So if you do find an issue, let me know. Okay. If you find a place where it's showing differently and wrong, let me know. Okay. And the SmartWorks is not necessarily actually off of this table. The SmartWorks is actually off of, they took Spectra and then they used the answer, which is then on NIST to generate the answer usually. That's how most people generate problems for spectroscopy, is there's already assigned spectra for almost every, for, thousands and thousands of molecules, hundreds of thousands of molecules that you can actually base problems off of. Okay, now we're going to look at a more detailed perspective for this stuff. Again, this one right here is going to be further down in that table. This would be like that step 4 on that table, where we're going to use the more specific information to determine more specific information about the molecule, right? And so, for example here, this right here would indicate you have a mono substitution here. This right here would give you an indication, some evidence that you have what's called a para substitution. So para substitution being where you have it on opposite sides of the ring. And the reason we're seeing a difference here is because when we look at this one here, it's going to be a degenerate. It's going to have the exact same energies for both sides, right? Because we can have them facing different directions here. Okay? And so this one here is going to have a difference in energies, which results in this set here, because you only have it on one side there. So depending on which direction this is facing at any given time, you're going to have a difference in energies. Okay? So that gives you that mono substituted where you have a doublet there. Okay? Now, one of the things you got to remember here is please don't take things from this spectroscopy and try to apply them when we get into NMR, okay? And vice versa. They're very different types of spectroscopy when we look at infrared versus NMR, okay, which we're going to be doing later. I've had a review on one of my publications where they tried to apply an NMR principle to IR and very clearly knew absolutely nothing about IR. And it caused havoc. So now I try to get you guys to. So this is that bending mode here for the mono substitution. And it gives you the split here. This one, on the other hand, for the para substitution, gives you a degenerate just one band. Okay, so let's talk about ultraviolet visible spectroscopy. This is another absorption spectroscopy. This is actually incredibly useful for determining conjugation. It's very reliable for determining conjugation. There's also a bunch of other uses for it, especially in like biological fields. Most likely, if you're using spectroscopy in biochemistry or the biological field, you're probably using this. Okay? Because it's actually quite cheap and easy, and you can put it in very small packages. Okay. And so what we're going to have here for an ultraviolet visible spectroscopy, we're going to have a source. If you're just doing visible, then you just need basically a light bulb. Okay? So you put basically a light bulb. You're then going to have a slit so that you can have your light nice and coherent. It's a nice coherent beam rather than being spread out and giving you different results depending on what it hits at. So now you have a nice coherent beam passing through that slit. So the next thing that's going to happen is you're going to use what's called the dispersion device this dispersion device is going to separate out essentially your colors. Okay? So it's going to divide your light by its frequency. Everybody's seen a prism where it does like the little rainbow? That's what that is. Rainbows are actually dispersion devices. It's actually the water and the air that's causing that dispersion. Okay? Okay, so you get your dispersion device. It's going to separate those into the different wavelengths or frequencies, right? And you're going to essentially have a little exit slit here, which you can move. So depending on where your exit slits moves to, you're going to select for a specific color, a specific wavelength range. Okay? And that's going to give you, I'm hitting my light with 520 nanometer wavelength light. Okay? You probably all have done something like this in terms of like general chemistry. You would have normally done it for like Beer's Law. Okay? Okay, so the next thing you're going to do is you have that specific monochromatic, meaning one color, wavelength of light. You're going to take that, you're going to pass it through a sample. Typically, this is going to be some sort of cuvette holding the sample. That's what this little square thing is. And that is then going to pass on to a detector. The detector's job is to read the intensity of what's coming into it. Okay? And so that's what it's getting in terms of the detector. The wavelength portion right here, where it's detecting what wavelength you're getting, is actually reading this portion, the exit slit usually. Okay? There's a few other ways of doing that. That's called a Fourier transform, but that's much more complicated. So I'm going to leave it to the simple selection one, which is the majority of instruments anyways, because they're cheaper. All right. So again, your sample is going to reduce that amount of light by some amount. If it doesn't absorb at all in that wavelength, then it's going to reduce that light by essentially zero, right? If it absorbs well in that wavelength, it's going to reduce that light by a lot more. Okay? Okay, so what is absorbance? Well, absorbance is going to be the negative log of the light incident. This is called incident light. That's why it's an I. But essentially, it's how, or a radiance, you can consider it. It's essentially the amount of light passing through. Okay? So you get right here, which is the amount of light that comes from the source. And then you're going to have the amount of light that's actually hitting your detector after passing through your sample. Okay? And so it's the negative log of the stuff that actually hits your detector after passing through the sample, divided by what the source would have been. Okay? This can actually be rewritten. This would be negative log. This right here is actually percent transmittance if we were to multiply that by 100 per percentage. Okay? So if you take percent transmittance and divide it by 100, you're actually going to get this. Okay? Okay, so let's look at some examples. So if we look at the, see this portion right there, that symbol? Lambda, capital lambda? Okay, that's the wavelength. Okay? If we put wavelength max here, that's your wavelength for your maximum peak. Okay? So your maximum amount of absorbance. Okay. And so what we're going to have here is we're going to see that our wavelength max here in the spectrum is centered at 217 nanometers. And so this actually corresponds right there to this conjugated system. And so what you're going to see here is you're actually going to change your wavelength max for this absorption depending on the conjugation of your system. Okay? And it'll also actually change a little bit by the substitution. So remember, whenever we're looking at these, what it is we're absorbing light, right? And they're moving electrons between orbitals here. Okay? And so what we're actually seeing is directly related to the energy of those orbitals, right? So if we make these orbitals more stable, they're going to be lower energy orbitals, aren't they? That we're moving from. Okay, so let's go ahead and look at that. You guys see that okay? Can you see it now? Oh my God, that really. Okay. So this right here would be a single double bond, right? A normal ethane right there. And we'd see the wavelength max would typically absorb somewhere in the 161 nanometer. Okay? It's pretty consistent. Now, if we just have an alkane or a cycloalkane, we're going to have an absorbance that's less than 150. Okay? Nanometers. What do we remember about wavelengths, by the way? Which higher energy? Large wavelengths or small wavelengths? Small. Exactly. Okay. So over here, we have a double bond that has another carbon off of it, right? See that? And so that's going to absorb at 177. Now, what if we have two double bonds, but they don't really have any interrelation? So they're not conjugated. Well, they're going to absorb at 178. Okay, so basically the same place that a single bond with one substituent has, right? With one alkane group off there. And so basically you just treat them as individual double bonds and your wavelength max doesn't change. They absorb at the same place. Okay? No real difference there. What if you have them conjugated instead, though? Well, that's going to increase your wavelength max. Okay? So this is a double trans conjugation, right? We have this going this way. Okay, and so that's going to be 217 for our wavelength max. If we have the cis on the other hand, right here, where we have the cis double bond there, again, it's going to be that conjugation. This is going to be 223. Notice the trans cis changes that wavelength max just a little bit, right? Typically about 5-ish. Okay. This right here is, again, a diene. This isn't a cyclohexane. And this is going to be a 256. Notice that's going to be trapped in this cis-cis configuration. This right here is further conjugated. See that? So we have 3 of these now. They're all conjugated together. And they're going to go all the way up to 274 for our wavelength max. Okay. You guys seeing those patterns now? Yeah, the more conjugated it is, the larger the number, right? Okay. Okay. So again, we're going to have here where we have a, this one here is a penta 1,4-diene. Again, we have 2 double bonds. They're separated. Notice we have a very similar number, right? When we have them conjugated instead with essentially the exact same structure, we get a large shift upwards in our wavelength max, which is 223 again. Now, formaldehyde right here, methanol, that's our aldehyde. You will notice that if we compare this to the previous double bond over here, this was 161. Now we have an oxygen in that double bond. This is going to be 280. So we see a huge shift upwards if we put an oxygen instead of a carbon. Okay? And if we have it just in a ring, period, so right there, no substituents. This is one substituent off of there. We can see that we get a pretty significant difference here of 182 versus something like 177, but not a huge jump, right? Because again, this is just the geometry around that's changing. It's not a conjugation. Okay. This would actually be a substitution alongside that conjugation we were talking about. So we further substituted this one. And notice that these are very similar, right? Because we have further substitution of this one on this one. These two. Oh, you can't see my deal anymore. I can't do both. Here. These two, they're almost the exact, right? And it's because it's just strictly the amount of substituents off those double bonds that's dictating those differences there. Okay. That's beta carotene, by the way. Remember the beta carotene we isolated? That's that right there. So that UV irradiation we did when we were doing these beta carotenes, that's why these beta carotenes showed up like they did under UV radiation. It absorbed the UV and then it re-radiated that out as partially as visible light. Okay, and so that's what we were actually seeing there. Okay, what time is it? I am out of time. Okay, you all have a wonderful day. We'll pick up here next time, and we'll use that conjugation effect. Okay? Right. Please make sure you practice the homeworks. So when you come in for the spectroscopy review next week, you'll have that sort of base knowledge. Left hand.
So me and Crystal were going to the tournament yesterday.